So, hello guys. Today I will present one which was published in CVPR 2022. As you may all know, recently there were published papers on vision transformers, especially DESTR, and some of its post papers like CDTR, but they are still lacking performance behind CNN-based detectors due to three reasons. The first one is that cross attention is used for both classification tasks together. Second one is that transformers decoder poorly initializes content queries. In DTR, they initialize it from scratch. That's why it can perform not so well. And the last reason is that self-attention poorly accounts for certain knowledge, which could help to improve inductive bias in the decoder part. So now let's turn to main contribution of the paper. The first contribution that the author proposed is to split cross-attention in two independent branches, one for classification and one for the regression part. As you can see here, this is the architecture of the decoder, and they use one branch for both regression and classification part, so that they predict from the shared features, while the authors propose not to share features, and so that they consider that classification and regression branches will likely focus on a different set of optimal features. In the below picture, you can see a cross-attention maps on the right. The A and B are cross-attention maps of DTR and CDTR, and as you can see, they have one branch of classification and regression, and they are more likely focused on shared features capturing both object and bounding box around this object, while on C and D pictures, you can see that DESTR classification and regression cross-attention maps differ. So in C, there is a classification cross-attention map, which highlights more cluster characteristic regions, while in D, as you can see, it has higher values on horizontal and vertical edges in the image, so that it guides the box prediction. So this was the first contribution that the authors made to the DESTR paper. The next one is wait. Sorry. Wait. Okay, sorry. So the contribution was in DTR, the positional embeddings are learned so that it can capture the distribution of objects in training images, while the content queries that are passed to the decoder part are inferred for every image from scratch. So authors propose to learn not only the positional embeddings, but also content embeddings by inserting mini encoder, as you can see on the right in the blue part. So after the transformer encoder part, they insert mini detector, which is used to predict a set of let's continue. As you can see, after to look at positional embedding, but also content embedding, so that they insert a mini detector. The feature of this object candidates used by detector classification can be passed to the decoder, and thus they initialize the classification, as we can see on the right. So having obtained the encoded images from the transformer mini detector, they pass them to the mini detector so that they can predict they call classification branch and regression branch. And using the positional encoding branch, they obtain embedding features which are used as input to the transformer decoder part. And the last contribution that the authors made is that they were seeking to incorporate prior knowledge in self-attention in the decoder part. So as you can see here in the DTR, on the right in the transformer decoder part, they use multi-head self-attention, which incorporates only self-attention to the one image, while authors want to, instead of computing self-attention for every query, they want to compute pair self-attention for every 2 pairs of queries. Each pair has been predicted to be spatially adjacent by the previous decoder stage. So the authors use IOU, intersection over union, to detect 2 objects that are spatially adjacent to each other, and then to compute pair self-attention between them. So that they think that it will incorporate much more information and useful features rather than self-attention to each of the query. Now let's come to specification of DESTR architecture. The first one would be mini detector. As you can see in the blue part, the input to the mini detector will be the encoder's last layer, which has a dimension h over w over c, where hw denotes the feature map size, and c is the number of channels. Mini detector uses these features to predict an object for every cell feature, and it predicts classification label and aggression of the bounding box center with height and width. After making the predictions for every, we select a subset of k predictions with the highest classification score, and this set of k predictions will be passed as initial object proposals to the decoder part. We obtain embeddings of these k proposals by using the formula below, where En is content embedding, which is obtained using concatenation between classification embedding features and regression embedding features. And Tn is positional embedding, which is obtained using using sinusoidal function. Next, we come to decoder architecture, which is mentioned in the yellow part. On the left part, there is a conditional DTR decoder layer, and on the right, it is DESTR decoder layer. As you can see, there is 3 main differences. The first one is that initial input to the decoder part is passed from the mini detector, and then they use pair self-attention instead of self-attention, and they have 2 branches split for regression and classification parts. Now, let's look into details for pair self-attention. For every object query A, which was obtained from the mini detector, they compute query key and value, where query and key are sum of content embedding and positional embedding, and value is a linear prediction of content embedding. They select pairs of queries or bounding box previous decoder output and encode this query. And below you can see the formula of computing self-attention between 2 objects A and B, which is the default formula for attention. Next, they compute formula for pair self-attention. They define L1 as a distance between the box center in B and the top left corner of the image. A is a object of interest, while A dot is a query which is the closest interest to this object. So they select and define PA based on the distance between query and closest query to this object. Then they compute pair self-attention using formula which is defined by A2, AB. And finally, they compute pair self-attention using the same softmax, but with different formula of attention and dividing by 4 multiplied by number of channels. And after computing both self-attention and pair self-attention, they combined together and added by add and NOR model. And the final formula looks as OA is equal to lambda multiplied by normalization layer of EA plus self-attention layer and plus the part of pair self-attention layer. And the last contribution that was made is split cross attention. So they split features after decoder self-attention layers. They split into two parts in classification branch and regression branch. For each of them, they use their own features of query and key, and they use the default formula of self-attention to calculate for both classification branch and regression branch. And this allows authors to make classification and regression branch not dependent from each other and obtaining more distinct and reliable features for prediction of classification label and regression bounding boxes. Coming to the results, we can see that by using these three main contributions and changing the architecture, the authors were able to achieve much better performance in all AP values compared to DETR, deformable DETR, anchor DETR, and CDETR. Yeah, that's it. Thank you for your attention.
Any questions? No questions. Okay,